Today we're going to be talking about lasers. A laser is a device that controls the way that energized atoms release photons. The word laser is actually an acronym for Light Amplification by Stimulated Emission of Radiation. This acronym very briefly describes how a laser works.
Although many types of lasers exist, all of them have a few essential features. In a laser, the lasing medium is pumped to move the atoms into an excited state. This pumping of the lasing medium is typically done by very intense flashes of light or electrical discharges that creates a large collection of excited state atoms or atoms with higher energy electrons. Generally, the atoms are excited to a level that is 2 to 3 levels above that of the ground state, which increases the degree of population inversion. Population inversion is the number of atoms in the excited state versus the number of atoms in the ground state. For a laser to efficiently work, large collections of these excited state atoms are required.
In the process of reaching this excited level, the electron absorbs some amount of energy. Just as it absorbed energy, it has the ability to release energy. The electron can simply relax, as this picture shows, and it is able to get rid of some energy. The energy that it emits comes in the form of photons, or light energy. The photons that are emitted have a very specific wavelength, which depends on the state of the electron's energy when the photon is released. Different wavelengths emitted produce different colors of light. Identical atoms with electrons in identical states will release photons also having identical wavelengths.
Another main key to making a laser work is a pair of mirrors that are located at each end of the lasing medium. The excited photons with very specific wavelengths reflect off the mirrors and travel back and forth through the lasing medium. In the process of doing this, they also stimulate or encourage other electrons to make the downward energy jump. This can cause the emission of more photons that have the same wavelength. This essentially produces a cascade effect, and many photons of the same wavelength and phase have been produced. As previously mentioned, there are 2 mirrors in the laser, one located at each end. The mirror at one end of the laser is half silvered, which means it reflects some light and also lets some light through. The light that makes it through is the laser light that is produced and we see.
Laser light is very different from normal light and has a few distinct properties. The light released is monochromatic, coherent, and very directional. Monochromatic light contains one specific wavelength of light and therefore produces one specific color. This wavelength of light is determined by the amount of energy released when the electron drops to a lower orbit. Coherent light is light that is organized. This means that each photon moves in step with the others and all photons have wavefronts that launch in unison. The light released is directional because the laser light has a very tight beam and is strong and concentrated. This is different than a flashlight, for example, which releases weak and diffuse light in many directions.
The ruby laser is one type of laser. Ruby lasers consist of a flash tube, a ruby rod, and 2 mirrors, one of which is half silvered. The ruby rod is the lasing medium and it is pumped by the flash tube. The flash tube is similar to what you would find in a flash camera. As the tube fires, it injects light into the ruby rod. This light then excites some of the atoms in the ruby. The excited electrons in these atoms emit photons as they fall back from their excited state. Some of these photons run in a direction parallel to the ruby's axis, so they bounce back and forth off the mirrors. As they pass through the crystal, they stimulate emission in other atoms. This creates monochromatic, single-phase, colonnaded light that leaves the ruby through the half-silvered mirror. Laser light!
This is a diode laser whose wavelength is 650 nanometers. As you can see, it is a monochromatic light with a coherent and directional beam.
This, on the other hand, is a flashlight. It has a diffuse light that is random and not focused into a beam. Now we are going to work on calculating the energy of a photon emitted from a hydrogen atom as it falls from its excited state. As we discussed, this phenomenon is what makes the light beam of the laser. To calculate the energy, we use this formula. In this formula, we multiply the Rydberg constant by the difference between the reciprocals of the final energy level squared and the initial energy level squared to get delta E, and the absolute value of delta E is the energy of the emitted photon.
So, here's a problem for you to work. Calculate the energy of a photon emitted from a hydrogen atom as the electron falls from n equals 3 to n equals 1. Remember this equation, where n is the initial n equals 3 and n final equals 1. What is the answer? Correct! The answer is B, 1.93 times 10 to the negative 18th joules. This is just one tiny photon that could be emitted from your own laser.